Hey everybody, 4.6 is logarithmic and exponential equations. We've been working with both of these types of functions. Now we're going to really look into the equations of both of the functions for the rest of the chapter, basically, 4.7 and 4.8 as well. So this is one of the rules. Recall that if you have y is equal to log base a of x, that's true if and only if x is equal to a to the y. That is the inverse relationship between logarithms and exponents. So that's going to help us solve logarithmic equations. Also, if you know you have the same base log base a of m and log base a of n, then you can assume that m is equal to n. This actually works the other way. If m is equal to n, you can actually go back this way and assume then that log base a of m is equal to log base a of n. That's applying the natural log to both sides of an equation, which I mentioned in class, and we'll talk about that. 15. So we're going to consolidate and write as a single logarithm first of all. So first I'm going to use the power rule for logs. And if you want to do this in one step, that's okay too. So just the power rule that the 3 can go on the inside. Now this is the product rule. Log base 2 of x minus 1 cubed times 4 equals 5. Okay, so now with that we have to basically free up the x. So if you free up the x, you can rewrite in exponential form. So we're going to go from logarithmic form to exponential form. So it's 2 to the 5th is equal to x minus 1 cubed times 4. Okay, so now we have an exponential equation, and we're going to continue this. So 2 to the 5th, well, I'm going to simplify that because I want to bring that 4 over. So it's 2 to the 5th over 4, which is equal to x minus 1 cubed. This is also 2 squared. So I'm just going to say, okay, that's 2 cubed. That's convenient, equals x minus 1 to the 3rd power. Take the cubed root of both sides. So that means that 2 is equal to x minus 1, add 1 to both sides. X is equal to 3. The last thing that you have to do is you want to check to make sure this satisfies the original equation in the original equation. So you're going to check in the domain. So in this, do you guys see that if you have 3 minus 1, that is greater than 0, and that's okay. So x equals 3 is your solution. You can write it like that if you choose. So the next equation we're going to solve is number 13's equation. It's a logarithmic equation once again. So consolidate. This negative right here I can bring to the inside, because that's 27 to the negative 1. So you can squeeze in a little negative 1 there if you're forgetting that that in fact is a power rule. So we can use that. Now notice that in this case, see that we have the same base, log with a base 2, log with a base 2. So that implies that the insides must equal. X cubed is equal to 27 to the negative 1. Okay, so if you want to, you can take the cubed root. I'm going to simplify this and rewrite it x cubed as 1 over 27. And even better, that's x cubed equals 1 over 3 cubed. Once again, we have kind of a nice, convenient numbers that we're working with. Don't get used to it. So x is equal to 1/3 when you take the cubed root of that. Check. Once again, make sure, and as you can see, if you put 1/3 in here, it's still positive, right? So it's okay. So it checks, and you're thinking of domain kind of in the equation. So for each of these logarithmic functions, so your solution is just 1/3. So on the left-hand side, when I solve number 26, I'm going to write as a single logarithm. So it's the quotient rule, x plus 1 over x equals 2. I'm I'm going to change colors just to show you. Remember that the natural logarithm, the base is e. So in this case, and each one has a different, you can either, if you have log something equals log something, you can set the somethings equal to each other. In this case, I would convert to exponential form. So go from log down to exponential form, and that's what we're doing right here. So e to the second equals x plus 1 over x. Now we're going to solve this equation, and I'm going to multiply both sides by x over 1 and x over 1, and I get e to the second times x equals, cancel those out, x plus 1. This is one of those tricky equations where you have x in two spots. So if you subtract x from both sides, you have e to the second minus x equals 1. I'm going to factor out, e to the second x right there. So I'm going to factor out an x on the next step, not on that one. So x is equal to e to the second minus 1, not x is equal to x times e to the second minus 1 equals 1. Now x is equal. Now we can say that 1 over e to the second minus 1. So that, well, if you approximate that just to check your answer, you'll find that it's actually a positive number and it's okay. Notice that x cannot equal 0 from the beginning, which is okay. We've got that covered. And x has to be greater than negative 1 because of this one. Remember with domain, x plus 1 is greater than negative 1. This is definitely going to be bigger than negative 1. I know it, so you can approximate it, but I would leave it exact and just be sure that it's not going to give you a negative in here or 0. So this is okay. So that's your solution, and that is fine. So number 30 is first consolidating, writing as a single logarithm. We have x squared minus 9 over x plus 3, and that's equal to 3. If you simplify this, which you can do, log base 4, you've got x plus 3 over x minus 3, and then that's x plus 3 here. So it's actually, we can write this in a simpler form, and I'm going to cancel this out and I'm going to show you why. If we know, for instance, that x cannot equal negative 3 in this, because that would be, from the beginning, that would make this side equal to 0. So it's okay to cancel that factor because we're excluding the idea that we know that x, that would be extraneous if that was in the solution anyways. So I just wanted to point that out. So now our simpler expression is log base 4 of x minus 3 equals 3, and I'm going to write that in exponential form. 4 to the 3 equals x minus 3. 4 to the 3 is 64. Equals x minus 3, add 3 to both sides, and x is equal to 67. And if you want to, just to make sure to check, it's obvious that 67 squared up here, 67 squared minus 9 is going to be greater than 0, and 67 plus 3 is also greater than 0. So it's okay to say that 67 is our solution. So now we're moving on to exponential equations. And this is just a little recall that if you know that you have an exponential equation where the bases are the same, then you can assume that the exponents u and v are equal. So to solve an exponential equation, this is like examples 4, 5, and 6, and I'm going to show you two different methods. The first method is to write in exponential form. Wait, it's already an exponential. You're going from exponential to log. So that means that it's log base 2 of 10 is equal to x. So you're done really right here, but what if you had to approximate, if you wanted to find out an approximation, and we don't have a base 2 in our calculator right off the bat on all calculators. So I would change the base. And I just want to show you. So x is equal to, I'm going to change it to natural log. So it's the natural log of 10 over the natural log of 2. Okay, then you could actually type this into your calculator. So that's why I kind of like method 2, and I find that this is the preferred for me anyways, is I'm going to apply the natural log to both sides. Because if you do it to one side, you have to do it to the other. Okay, so I'm going to take the natural log of 2 to the x, and I'm also going to take the natural log of 10. So that's our first step. Second step is use properties of logs to solve. And the property of log that I want to use is the power rule. Okay, so this x can go out front, so I can rewrite this as x natural log of 2 equals natural log of 10. If I divide now both sides by natural log of 2, I get that x is equal to ln 10 over ln of 2, which is the same answer that I had from method 1 once I changed the base. Okay, so for number 41, I'm actually going to apply the natural log to both sides, and that's what method 2, what I showed in the last example. So by doing this, this is an exponent. I can bring it out front, and same with this x right here. So I have 1 minus 2x, that's in parentheses, times the natural log of 3 is equal to x natural log of 4. Okay, next step, I'm going to distribute this natural log of 3 to both. So I have natural log of 3 minus 2x ln 3 equals x ln 4. So now what we're going to do is we're going to get all the terms with x onto one side. So I'm going to bring, I think I'll just bring this guy over here. So it's natural log of 3 equals x ln 4 plus 2x ln 3. Notice that x is a like factor in both of these, so let's do that. I'm going to change the colors. See x and x, so factor x out. So it's x times ln of 4 plus 2 ln 3 equals natural log of 3. So now what I'm going to do, sorry we're getting crooked, is I'm going to divide both sides by ln of 4 plus 2 ln 3, and I get that x is equal to the natural log of 3 over ln 4 plus 2 ln 3. And that's your final answer. Okay, once again, I'm going to apply the natural log to both of these. And properties of logarithms, do you see that we have a product right here, 5 times 2 to the 3x. So it's going to be the natural log of 5 plus the natural log of 2 to the 3x equals the natural log of 8. Now I have a power, 3 to the x can come out front, so it's the natural log of 5 plus 3x ln 2 equals natural log of 8. So this is the only term, right, with an x in it. So subtract that natural log of 5, bring it over to the other side. So you have 3x ln 2 equals ln 8 minus ln 5. Divide both sides by 3 ln 2. Cancels that ln 2 and this 3. And I have to do it to this side, so that is 3 ln 2 as well. So x is equal to, and you can consolidate that if you want to, but you can also keep it as ln. So is everybody okay with me doing 8 over 5 on the top and then 3 ln 2 on the bottom? Either way, it would be fine in your calculator. So start getting used to the idea of maybe inputting this into the calculator, because when we start doing application problems, you're going to need approximate answers. So number 88 gives two functions, f of x and g of x, and the first step is to solve f of x equals 2. So you set log base 3 of x plus 5 equal to 2. We're going to solve this logarithmic equation by converting it to an exponential. 3 to the second is equal to x plus 5. Just subtract that 5 and bring it over here, so that means that x is equal to 9 minus 5, x is equal to 4. Once again, make sure that that's not extraneous, and it isn't in either of these. Part B, g of x is equal to 3. So we're going to take log base 3 of x minus 1, which is g of x, and set it equal to 3. So I have 3 to the third in exponential form equals x minus 1. 3 to the third is 27. Add 1, that's equal to x. So x is equal to 28. Once again, that's not extraneous. Part C, solve f of x equal to g of x. So now we've got log base 3 of x plus 5 equals log base 3 of x minus 1. So once this is the kind of property where if you have the log of the with the same base, you can set the inside stuff equal. X plus 5 equals x minus 1. Now when you solve this by subtracting x from both sides, you get 5 equals negative 1. That's a contradiction. So that means there is no solution. Okay, that's like two linear equations. They're both parallel. They'll never intersect. So it's not possible. No solution. So these two functions will never intersect, the two logarithmic functions. Just a reminder, remember what a logarithmic function looks like? Goes through usually this point. If the base is greater than 1, 1, 0, just keep that in mind, visualizing. Now this is a good review. I didn't do E because I think it's very similar to D. So remember what this means from chapter 1, f of x plus g of x equals 3. That's the same thing, so the sum of two functions. So we're going to take L log base 3 of x plus 5 plus the log base 3 of x minus 1, and it's equal to 3. So this is the product rule because it's a sum of the logs is equal to the log of the product. So now we have x plus 5 times x minus 1 equals 3. Now I'm going to convert this to exponential form. So we have 3 to the third equals x plus 5 times x minus 1. So I just continued this on another page to give us some more room. What does this smell like? It smells like a quadratic to me. So 3 to the third is equal to 27. And if I FOIL this or expand it, I get x squared plus 4x minus 5. So I need to solve this by getting it into standard form. That's the best method. Subtract 27. So x squared plus 4x minus 32 equals 0. Try to factor this if possible. So x, I think it's going to be an x, and I think it's going to be an 8 and a 4. And it looks like the 8's going to be positive and a minus. So x equals negative 8 and x is equal to 4. But you need to check your solutions, okay? X minus 8 ends up being an extraneous solution because if you check it up here, you have negative 8 plus 5, which is equal to negative 3. You can't take the log of a negative number. So that's extraneous. Our only solution left is 4. The last example I'd like to do is number 50. I put smells like, smells like, because it kind of looks quadratic-like, doesn't it? So one tricky way to solve this type of equation is if you do a little fancy math, you can say let u equal 3 to the x. Okay, so believe it or not, this kind of works because this ends up looking like a quadratic. If I rearrange this, I'm going to write this as 3 to the x because properties of exponents, 2 times x is the same as raising 3 to the x to the second power. Plus, we just have 3 to the x minus 2 equals 0. So now I have u squared plus u minus 2 equals 0. So now if I try to factor this, because it's a quadratic, I can do that by saying u plus 2 and u minus 1. So that tells me that u is equal to negative 2 or u is equal to 1. We're not done though, because now we have to substitute 3 to the x back in for u to find what x is. So 3 to the x equals negative 2. Is that possible? Can an exponential function give me some x value that makes that equal to negative 2? Not possible. Okay, and now if we do this one, 3 to the x is equal to 1, so we can cancel this guy out. Well, if you think about that, what's the only thing that x can be? And we can also, if you want to apply the natural log, you can do that, but x must equal 0, right? Because this has got to be raised to the 0 power. Okay, if you applied the natural log, you'd have ln of 3 to the x equals ln of 1. ln of 1 is 0. Okay, so you're going to bring this x out front, so you have x natural log of 3 equals 0. Divide both sides by natural log of 3. That gives you x equals 0. So that's just an alternative, or just by observation, you can say that x must equal 0. Okay, that's the end. I'm sorry, this is a little rough around the edges. I didn't get a chance to edit it much, but I hope that it helps for this lesson. On Friday, I plan to do some problems like this, similar to this in class for you guys to practice. We've also got a quiz, and we're also going to start looking at problems in 4.7. 4.6 is due on Monday, and 4.5 will be due on Friday. I'll see you all Friday. Bye.